Hello everyone, today I will be introducing my twin project, a 2D Truss finite element analysis using a parallel implementation in C++ and Eigen. The goal of this study is to simulate 2D truss structures composed of bar elements, calculate nodal displacements, internal forces, stresses, strains, and support reactions, and export the analysis result to CSV for further visualization. To improve performance, we implemented a parallelized solution process. Inputs include node coordinates, boundary conditions, and applied external forces. Element data includes material properties, such as Young's modulus and cross-sectional area. Outputs include extrusion time, nodal displacement vectors, element internal forces, stresses, strains, and support reactions. We simulate large truss structures, such as a 50 by 50 node grid. Nodes and elements are automatically generated by the program. The leftmost nodes are fixed in the x direction. The bottom nodes are fixed in the y direction, and gradient external loads are applied to simulate real structural loading conditions. This is the node structural definition, including position, fixation status, external force, and reaction force. We use a structure for storage and easy manipulation. This part is simple but crucial. The element structure records the connected nodes, length, direction cosines, stiffness, material properties, and computes stress and strain results. It provides the basis for subsequent stiffness metrics and internal force calculations. This code automatically creates nodes and connecting elements based on user-specified node count and spacing, supporting the inclusion of diagonal members. This allows us to quickly build large-scale structures and flexibly control boundary conditions and element configuration. To simulate real loading conditions, we apply x direction loads from bottom to top on the right boundary, and y direction loads from left to right on the top boundary. This function automatically distributes gradient loads according to coordinates. Here, we calculate each element's length, direction, and stiffness constant. This data is used to generate the local stiffness matrix for each element and is fundamental for assembling the global matrix. Each element's local stiffness matrix is calculated based on direction, cosines, and mapped to the global stiffness matrix. The slide also shows the 2D truss element stiffness matrix formula. In implementation, Eigen's metric operations greatly simplify the code. This is the core of parallelization. We use OpenMP to parallelize LU decomposition for solving large sparse linear systems. The code can dynamically adjust the number of threads, effectively accelerating the displacement solution process. After obtaining nodal displacements, we can deduce the deformation of each element and calculate internal forces, stresses, and strains. We use the classic 1D bar formula and implement it in vectorized form for efficiency. The final results include nodal displacements and element stresses, which are exported as CSV files. The figure shows an example output. Make it easy to visualize and analyze it with Python or Excel. This slide summarizes the overall process, from data reading, element property calculation, metric assemble and solution, result calculation, to output. The entire process is automated and supports parallel acceleration. This is actual simulation deformation diagram, clearly showing the deformation trend of the structure under load. Red arrow indicate applied external forces. The redder the member, the greater the tension. The bluer, the greater the compression. This is my reference. Thank you for your listening.